Hello Math 109 students. We are going into section 3.3 with this video. Again, chapter 3 is about the graph of a function, characteristics of the graphs of functions. So just some definitions here to begin with. Even and odd functions. A function is even if for every number x in its domain, so every number in the domain being the inputs, the number negative x is also in the domain, and when negative x is the input, you get the same thing as when positive x is the input. So the outputs are the same whether you put in -2 or +2, you'll still get 10. So you'll have the point -2, 10 and +2, 10. Those will both be points on the graph. That's just for example. All right. A function is odd if and only if whenever the point x, y is on the graph, then the point -x, -y is also on the graph. Okay, so on the previous one, it would have been x, y, and -x, y. But this time it's x, y, -x, -y. So a function is odd if for every x in the domain, for every input, the number -x is also in the domain, and whenever you plug in x, if you plug in -x, you don't get the same thing, but you get exact opposites. So if you put in x, you'll get the opposite value than if you plug in -x. So, for example, if you get to 10, then if you do -2, you'll get -10. Or if you have 1, -100, if you plug in -1, you'll get +100. And so on and so forth. All right, a function is even if and only if its graph is symmetric with respect to the y-axis. Symmetric with respect to the y-axis. Okay, so that would be something like, oh, I did not do that very well. Something like, it's hard for me to do this, like that. So that here's the y-axis. If you fold it on the y-axis, the function folds onto itself. It's a mirror image on the y-axis. All right, a function is odd if and only if its graph is symmetric with respect to the origin. So this is axis symmetry versus point symmetry. The origin is a point. All right, so for a point, it's like something like this. So here's the origin. It means that you can rotate around that point like a merry-go-round. Here's the center of the merry-go-round. Rotate it 180 degrees. 180 degree rotation, and it becomes the exact same picture it was before you rotated it. So the first quadrant goes all the way to the third quadrant. The third quadrant goes all the way to the first quadrant, and they become the same thing. And it would be the same thing for the second quadrant and the fourth quadrant as well. All right, we're gonna look at that some more. An exercise that I like to do with students with even and odd, just to build an intuition about it, get a feel for it. Graphically, if you're looking at an even or odd function, take the letters of the alphabet, capital letters. So A, B, C, you know the letters of the alphabet, the capital letters. And I want you to think of all the letters and describe them as even, odd, neither, or both. Okay, even, odd, neither, or both. A function can't be both. But a letter of the alphabet is not a function, right? It doesn't pass the vertical line test. So a letter of the alphabet could be even and odd at the same time. But the graph of a function could not be. But for the sake of this exercise, I want you to think about it like that. All right, pause the video and go through all the letters of the alphabet and classify them in your mind, and then we'll go over them together. Okay, so A would be even. Why? Because A is symmetric about the y-axis. If you put a y-axis through the letter A, it's a mirror image of itself on this side, on the left and on the right. All right, so A is even. What about B? B is neither. C is neither. D is neither. A, B, C, D, E is neither. F is neither. Now E and C would be symmetric about the x-axis, right? If you put an x-axis through here, it would fold onto itself. If you did that with E, it would fold on. But that doesn't count. All right, for it to be even, it has to be symmetrical about the y-axis, not the x-axis. E, F, G is neither. What about H? H, I bet you're going to say even, and it's not that you're wrong. You're just not completely right. H is both. All right. If you cut it in half, you can cut it in half, and it's 2 equal halves. But also, you could rotate it about the origin, about the center point on the H. You could rotate it 180 degrees, and it's the same exact thing it was before. E, F, G, H, I is both as well, for the same reason. J is neither. K is neither. H, I, J, K. L is neither. M. What about M? M is even. It's not both, because if you rotate it 180 degrees, it's not an M anymore, it's a W. What about N? N is odd. It's not even, right? Because you can't split N in half, right? If you try to cut it in half, this corner doesn't have a matching corner up here, right? It doesn't have that. Same thing for, so it's not even, but it is odd. If you were to rotate N about the point right there in the center of it, rotate 180 degrees, it's going to be the same picture. It's going to be the same letter. H, I, J, K, L, M, N. O is both. P is neither. Q, I'm going to P, Q. Q is neither because of that curly Q right there. Makes it neither. R is neither. S, what about S? S is odd for the same reason that N is odd. Q, R, S. T, T is even. U, well, it depends. If you draw a U like this, it's even. But if you put the tail on the U like that, then it's neither. T, U, V. V is even. W is even. Same reason M is even. X is both. Y. Depends on how you do a Y. If you do a Y like that, then it's even. If you do a Y like this, then it's neither. Z is odd. All right, Z is odd. So that just to help you think about, get a feel for even and odd functions, looking at them on the graph. These, just do this example right here in your head. Look at these 3 graphs and describe them as even, odd, or neither. All right. This first one is even. This second one is neither. All right. It's neither because if you rotate it 180 degrees, there's nothing in the 4th quadrant, right? There's nothing down here, but there's something in the 2nd quadrant. And so when this goes to the 4th quadrant, it's not going to be the same picture. What about this one? This one's odd because this 1st quadrant and this 3rd quadrant are mirror images of each other. And you rotate 180 degrees, it becomes the same picture as it was before. All right, what about identifying even and odd functions just by looking at the equations? We can do that as well. Now, the instructions say to use a graphing calculator to decide, and you can do that. If you have an equation, you can type in your calculator and you can look at it, and you could probably tell whether it's even or odd that way. But I do want to teach you how to be able to just do it according to the equation. All right, so think about the definition. What we want to do for an even function, f of negative x is the same thing as f of x. For an odd, that's even. For odd, f of negative x, f of negative x is equal to the opposite of f of x. So we're going to test that out. So for this part A here, I'm going to plug in negative x. I'm going to plug in negative x in the place of x. So that becomes negative x squared minus 5. So that's going to become, what's negative x times negative x? It is positive x to the second minus 5. So now compare this to this. It's the same exact thing. So when we plug in negative x, we get the same thing as f of x. So it's even. All right, part B. G of negative x. It's going to be negative x to the third minus 1. So that's going to be negative x times negative x times negative x is a negative x to the third minus 1. Now, is this the same as what we started with? No. Is it the exact opposite of what we started with? It is not. It is also not the exact opposite. Because, look, this is a negative 1, and this is a negative 1. So it's not the exact opposite. One of the terms is opposite, but the other term is the same. It's not. So it's not the exact opposite. All right. So just want to show you that. So this is neither. Part C, we're going to do h of negative x. That's going to be kind of out of room there. 5. That was negative x to the third minus negative x. So I plugged in negative x in the place of x. Again, negative x to the third. Negative x times negative x times negative x is negative x to the third. And we multiply that by 5, we get negative 5x to the third. Minus negative x is plus x. So compare it. Is this the same? No. Is it the exact opposite? Yes. Because look, that term is the exact opposite of that term. And that term is the exact opposite of that term. So it is the exact opposite. So that means it's what? Odd. Now, there's a shortcut trick to this as well. But I have to teach you something, or at least convince you of something before the shortcut will be any good. I need to convince you, first of all, I need to convince you to think of 0 as an even number. Think of 0 as an even number. Here's why you should think of 0 as an even number, right? 10, 8, 6, 4, 2. Are all these even? Yeah. What's the next number in the pattern? 0. 0 should be thought of as an even number as well. And if also, as you're counting up, right, everything that ends in a 0 is an even number. So the double 0 should also be an even number. So that's one thing I want you to be convinced of. The second thing I want you to be convinced of is that a constant is the same thing as having x to the 0. So let's say you had x cubed plus 2. That's the same thing I want to convince you. That's the same thing as x to the third plus 2x to the 0. Now why? Because x to the 0 is what? Anything to the 0 power is 1. Anything to the 0 power is 1. Okay, that may seem strange. I want to convince you that that's true and that makes sense. Here's why. Let's say you have x to the 50th over x to the 50th. You remember what you do when you divide like bases? You subtract their exponents. So this becomes x to the 50 minus 50. Well, what's that? That's x to the 0. But what is anything over itself? Anything divided by itself is 1, which is why x to the 0 is 1. Anything to the 0 is 1 for that reason. So those two things I want you to consider. I want you to consider that 0 is an even number and that a constant is the same thing as having an x to the 0 with that term. If you can think of it that way, then here is the shortcut. For if all exponents are even, then you have yourself an even function. If all exponents are odd, then you have yourself an odd function. If there's a mixture of even and odd exponents, then you have yourself a function that is neither. So now let's look back at our example and do it that way with the shortcut. All right, look at this first one. That's an even exponent. And this is the same thing, remember, as x to the 0. That could be an x to the 0 right there. So that's also an even exponent. So they're both even exponents. So that is even, which is what we said before. All right, on part B, what's that one? That's an odd exponent. What's that one? Well, that's the same thing as having an x to the 0, which is an even exponent. So it's a mixture. So this one's what? Neither. Same thing we said before. We'll look at the last one. All right, this is a what? That's an odd exponent. That second one is an x to the what? It's the same thing as x to the first. So that's also an odd exponent. So both of them are odd, so what is it? It's an odd function, which is the same thing we said before. Next order of business in this section is intervals of increase and decrease and constant, and also defining extrema, like the maximum and minimum of a function. All right, so think of little Mario, all right, running across the screen, and if he's running downhill, here's little Mario. Ooh, that's a bad little Mario. Okay, if he's running downhill, then he's decreasing. He's running from left to right every time. Okay, if he's running flat, he's constant. If he's running uphill, he's increasing. Now, we always give our answers for intervals of increase in terms of x, in terms of the x values. It says in terms of the domain is what it says. So that always gets students confused every time. We're looking to see if it's going up and down, up or down. But as we give the answer, we're only giving the x values for where that occurs. We're talking about where it's increasing and decreasing, which is the x values. So this thing is, so this thing is decreasing throughout here. All right, but how do we give the answer? We say it is decreasing from what value of x to what value of x. When did it start to decrease? Well, how far to the left do you want to look? We can look all the way to where? To negative. It started in decreasing way back at negative infinity. When does it stop decreasing? It stops decreasing right here. What do we say? I guarantee you're going to want to say 1, because that 1 is just sitting there saying, pick me, pick me. Don't do it. We always look at the x-axis, look at the x value to tell where it is decreasing. We say from negative infinity to 0. All right, then we say it is constant. It's constant from what to what? From there to there. And what are those x values? From 0 to 2. We always put parentheses on these things too, never brackets. Why? Because at the place where it stops, is it decreasing there or is it constant there? You can't, at that exact instant, it is undefined whether it's decreasing or constant because it's transitioning right there. All right. And lastly, we say it's increasing from there to where? Well, all the way, right? All the way, forever. Well, how far is forever? Forever. To what? To infinity. So from what to what? From 2 to infinity. All right, try to answer this one. Intervals of increase and decrease before we go on. Okay, so it is increasing all throughout here. So we're going to say it's increasing from where on the x-axis to where on the x-axis? Well, from all the way back here. So from negative infinity, where it's increasing from negative infinity to where? To negative 1. All right, then it's decreasing from all throughout there, right? From where to where? From negative 1 on the x-axis to where on the x-axis? To positive 1 on the x-axis. Then it's increasing again from there, all throughout there. So from That's why I put it here with a union symbol. From 1 as far that way as you want to look to infinity on the x-axis. Okay. As we said. Try to answer this one. Okay. Hopefully you've answered it. It's increasing from negative infinity to 0. Now, again, I bet you wanted to say 1, didn't you? Don't pick that 1. Look on the x-axis, not the y. It's increasing from negative infinity to 0. It's constant from what to what? From 0 to 2. Then it's decreasing from what to what? From 2 to infinity. I bet you some of you wanted to say negative infinity because you say, well, it's going down to negative infinity. Yes, it is going down to negative infinity, but it's also going to the right to positive infinity on the x-axis. Negative infinity on the y, but positive infinity on the x. And you're always answering in terms of the x. All right, answer this one. Increasing and decreasing. Go ahead and pause it. Okay. Hopefully you've answered it. It is decreasing from negative infinity to 0 and from 2 to infinity. So throughout here, negative infinity to 0 and here to here, which is 2 to infinity. And it's increasing from 0 to 2. So from here to here, from 0 to 2 on the x-axis. All right, next concept these are called extrema. Extrema, okay? Extrema. But extrema are broken down into minima and maxima. Minima is just the plural for minimum, which is the singular. All right, but there are two types. There are relative minima and maxima, and there are also absolute minima and maxima. What's the difference? The relative minima and maxima are all of the low points and all of the high points. So every time you have the top of a hill, you have a relative maximum. Every time you have the bottom of a hill, you have a relative minimum. Think of it as like the fastest person in every city is a relatively fast person. They might not be the maximally fast person. They might not be the fastest in the world, but they're fast compared to the people around them. These points are the highest points compared to the points directly around them. But even though they might not be the highest point on the whole graph, they're higher than the points directly beside them or lower, depending. All right, whereas the absolute is the lowest point and the highest point. So now a point can be both relative and absolute, right? The fastest person in the world was also the fastest person in his city, so he was locally fast, but he was also universally fast. Another name for relative extrema is local extrema. Local and relative are the same, are synonymous in this case. All right, looking at this one, give me the local or relative extrema. Like give me the local maximum. The local maximum is right here. So the easiest way to do that is to give it as an ordered pair. Just say the local maximum is -1, 2. Okay? And the local minimum is right there, or relative minimum, is at 1, -2. Okay? Now, to be more thorough with your answer, you could say this. You could say we have a local maximum of 2 when x equals -1. So the local maximum is, local max is 2. So the is the y coordinate. The when or where, or you could say where, same thing, is the x coordinate, where x is -1, or at x equals -1. All right, you say we have a relative or local. Local and relative are synonymous. Relative minimum is what? -2 at x equals 1. Or when x equals 1. Same thing. All right, try to do all these about this graph, and then we'll do it together. Okay. The domain, remember the domain means all of the x values that are involved in the function. All of the x values that are somewhere represented in this function. Okay. I think I should have said this before, even though the PowerPoint didn't actually say it. What about the absolute max and min? Okay. The absolute max and min for this function. This is a relative maximum, but it's not the absolute maximum because this function keeps on going forever, right? It goes up out of the screen forever. So some might say that the absolute maximum is infinity, but we're not going to say that. This particular textbook says that it does not have an absolute maximum because it never reaches a highest point, which is kind of another way to say that. All right, what about the absolute minimum? Similarly, the absolute minimum is negative infinity, but we won't say that. We're going to say it doesn't have one because it never reaches the lowest point. All right, now try to answer all these questions. All right, the domain here is all the x values, every single x value on the x-axis, all real numbers, negative infinity to infinity. What about the range? Also all reals, negative infinity to infinity. The zeros is where it crosses the x-axis. Zeros are -2 and 1. You might say -2 twice because when it hits the x-axis and turns around, that's called a double root. You actually, if you were to solve the equation, you would get that answer twice. The y-intercept is -4, or you could say 0, -4 if you want to give an ordered pair. The absolute maximum, it doesn't have one because it goes on forever. The absolute minimum is also none. The relative maximum would be what? Right here. -2, 0 if you gave the ordered pair. And the relative minimum is 0, -4, again if you gave it as an ordered pair. All right, where's the function increasing? It's increasing all throughout here, which is from negative infinity to -2. And it's also increasing from here to here, which is 0 to infinity. You'll want to say -4, but don't do it. And it's decreasing right there from -2 to 0. All right, do the same thing here. Again, the domain, all reals. The range is not all reals this time. The range doesn't get any lower than -4, so it goes from -4 to infinity. Notice we have a bracket on the -4 because it actually touches the -4. The zeros are what? -2 and 2. The y-intercept is 0, -4. The absolute max doesn't have one. It's none. But the absolute minimum, there is an absolute minimum right here. That is the absolute lowest point on the graph, and it is 0, -4. What about a relative maximum? It doesn't have a relative maximum, but it does have a relative minimum, and the relative minimum is the same thing as where the absolute minimum was, 0, -4. Where is it increasing? It is increasing from here to forever. So from what to what? 0 to infinity. And it is decreasing starting at negative infinity all the way to there, so from negative infinity to 0. Try to identify the local and absolute minima and maxima for these graphs. All right, for part A, we have a local minimum at 0, 1. We have a local maximum, I should say MIN, local maximum at this point and at this point. So at 3, 6, and at 5, 5. Now, maybe I wasn't clear here. Notice that these graphs end in points. They don't end in arrows. So we assume that they stop right here. Okay, that's why those are local minimums, because this is lower than any point near it. This is higher than any point immediately near it. All right, what about an absolute max? Absolute max would be what? Would be that point. That's the highest point. So 3, 6. 3, 6 is a local and an absolute max. What about the absolute minimum? That would be there, 0, 1. All right, part B. Local min would be, it doesn't have one. And that's kind of, okay, this is going to take some explaining. right here, right there. It's an open circle, which means it doesn't include that point. All right. Well, how close does it get to that point? It gets infinitely close to that point. So however close to that point you can imagine, you can still get closer. So you can say, well, I can get 2.99999, 1.00000000001, but you can get closer still, right? You can just add another 9 and put another 0 in there. So you can. It doesn't have a local minimum because you can't. It never reaches a local minimum. It always gets lower, and that is so mind-boggling to think about. Infinity just completely destroys our imaginings that we know anything. All right. So it doesn't have a local minimum. It has a local max. It has 2 of those. 1, 2, and 5, 3. Absolute minimum. Again, none. For the same reason as there's no local minimum. Absolute maximum would just be that point, just 5, 3. Okay, part C. We have a local minimum. Where? We have a local minimum actually all throughout there. So our local minimum value is this value, which is 1 on the y-axis. So we have a local minimum of 1 at x within this interval. That little symbol right there means within the interval 1 to 2, when x is within the interval from 1 to 2. So we have a local minimum of 1 when x is between 1 and 2. All right, we have a local maximum at 0, 3 and at 5, 4. We have an absolute maximum. We have an absolute minimum. That's going to be the same exact answer as my local minimum. We have an absolute maximum only there at 5, 4. All right, part D. We have a local minimum at 0, 0. We have a local maximum. We don't have one actually, because it continues on forever. Absolute minimum is also 0, 0. Absolute maximum is none, also none. Okay, part E. Local minimum. We don't have a local minimum, none. Local maximum at 1, 4, but nowhere else. Absolute minimum is none. Absolute maximum is also none, because it goes up forever on that part. This time I am given an equation here, and I'm told to the equation of a function to use a graphing utility to approximate the local maximum and local minimum, and also from there to determine the intervals of increase and decrease, because that has a lot to do where you have with local maximum and local minimum. Whenever you have a local maximum, you have stopped increasing and you begin to decrease, and vice versa for local minimum. So I'm going to graph this in the this TI Smart View software. This software, you can have a free license to this software if you just Google TI Smart View. You can have a free trial version for like 90 days, but after that it costs you like $100 or something like that. All right, so I forgot what I'm typing in. 6x cubed minus 12x plus 5. 6x cubed minus 12x. Oh, shoot. 6x cubed. What in the world? What are you doing? You are not clicking when I'm telling you to click. Minus 12x plus 5. Make sure that's right. Minus 12, yeah. And it says for x between -2 and 2. So for x between -2 and 2. So that tells me that my window needs to be, x min needs to be -2. The x max needs to be 2. I'm going to let my x scale be 1. I'm going to do my y min and max. I kind of got it a little funny here from a problem I was doing earlier. I'm going to let my y max be -10 as in the standard window, and the y max be 10, and the y scale be 1. I may have to adjust this in a minute once I see what it looks like. Yeah, I want to see a little bit higher than that, don't I? I need to be able to see that top point there, that local maximum there. So I'm going to go back to window and I'm going to increase the y max to, let's try 15 and see if I can see it then. Yeah, I can see it now. All right, so I can actually, I don't even have to approximate it. I can find that local maximum right there by hitting second calc. Option 4 is maximum. For the left bound, I need to scroll to the left until I know I'm to the left of that point. All right, that's good enough. Enter. Right bound, I scroll to the right until I know I'm to the right of that point. That's good enough. Enter. Just hit enter again for the guess, and our maximum is -0.82, 11.5. All right, let me write that down. Max, local max, -0.82, 11.5. Okay. Now, let's find the local min, second calc. Minimum. All right, the left bound just needs to be anywhere to the left of it. That should do fine right there. The right bound needs to be anywhere to the right of it, so that should be fine right there. Hit enter again. Now hit enter for the guess. Just hit enter again, or you could go down there and guess it, but the minimum is 0.82, -1.5. Local max, sorry, local min, 0.82, I can't remember what it was. What was it? -1.5. -1.53, or just -1.5. Now, okay, that's what it looked like, right? Okay, what are my what is my interval of increase and decrease then? My interval of, it's going to be an interval of increase from -infinity to that x value right there, which we found was -0.82. And I have an interval of decrease from that point to that point, which would be -0.82 to +0.82. Then I have an increase again from there to, from +0.82 to infinity. From 0.82 to infinity. But there's one correction I need to make, because it says only for this part, for -2 to 2 on the x. So let me change, that means I'm not going from -infinity to -0.82, because I don't go any farther left than -2. So I really need to put from -2 to -0.82 there. And again, I'm only going not to infinity, but to 2. So 0.82 to 2 right there. All right, next concept will be the average rate of change. The average rate of change of f from A to B is defined this way. All right, it's the change in y over the change in x. Now you've seen this before. You've seen an equation like this before. It just looked different. Okay, this is the same thing, all right, as, let me show you. Let's say you had this parabola. All right, let's just pretend this is a parabola. Okay, and you have these 2 points. We're trying to find the average rate of change. Like how much did this function change over this interval? By an average of what, right? So what we're doing with an average rate of change is we are finding the rate of change as if it were a line instead of a curve. So we're finding the rate, basically we're finding the slope of this line, and that's the average rate of change of the curve from this point to this point. So let's say that that this is the point A, F of A. Okay, A and F of A, which is the y coordinate, right? So, and let's say this is the point B, F of B. This is the point B, F of B. Then if we do the slope formula, we end up here. Y2 minus Y1, that's F of B minus F of A, right? That's Y2 minus Y1, basically. That's F of B minus F of A over X2 minus X1. Well, that's B minus A, X2 minus X1. So that's what this formula is. It's the slope of the line that connects the 2 points on a curve that we're interested in. So example 7, find the average rate of change of this parabola. Part A is from 1 to 3. So all we do is we find the 2 points. We find the point when you plug 1 in for x, so like f of 1 would be 3 times 1 squared, which is 3 times 1 squared is 1, which is just 3. And f of 3 is 3 times 3 squared, which is 3 times 9, which is 27. So I have the point 1, 3, and the point 3, 27, and I'm finding basically the slope between those 2 points, which is the average rate of change of this parabola between those 2 points. So we do 27, here they already did it for us right here. 27 minus 3 over 3 minus 1, which is 24 over 2, which reduces to 12. All right, you can do the same exact thing with these numbers. Just well, we've already done f of 1. That's already done. That's going to be the point 1, 3 again. But now plug in 5, and you'll get a second point, and you'll find the average rate of change. That's what they're doing here. All right, so I'll let you look at this example here, already done. And I think showing you this one will probably suffice for you knowing how to do parts B and C because it's done the same way. All right, so this illustrates the point here. Okay, so you have the point 1, 3, and here's the point 3, 27, and here's the line running between those. All right, then the next, so the average rate of change between those 2 points is the slope of that line, whereas the average rate of change between 1, 3, and 575 is the slope of this line, which is steeper. And between 1, 3, and 7, 147 is the slope of this line, which is even steeper. So you can see for the curve, the average rate of change is going to depend where you are on the curve. The farther along you get on this curve, the higher the rate of increase is going to be. So the average rate is going to increase the farther you go along the curve. All right, so which brings us to the next topic, which is called the secant line, a very related topic. The secant line, that's the line. A secant line means it's a line that goes between 2 points. It intersects a curve or a circle or whatever at 2 places. So if you're talking about a circle, this would be a secant line, as opposed to a tangent line. A tangent line intersects a circle at one place. It just touches a circle at one place, whereas a secant line touches a circle at 2 places, or a curve. More like a curve in this case. All right, so to find the slope of the secant line, you do exactly what we just said. All right, f of b minus f of a over b minus a. So let's apply that skill to this example here. We have a function g of x, and it says find the average rate of change of the g function from -2 to 1. So what I do is I find g of -2. I plug in -2 for x. I get 3 times -2 squared minus 2 times -2 plus 3. That's going to be -2 squared is 4, so 3 times 4 plus 4 plus 3. That's 12 plus 4 plus 3, which is 12 plus 4 is 16 plus 3 is 19. So I have the point -2, 19 as 1 point. Then I also plug in 1, so I also find g of 1. And that's going to be 3 times 1 squared minus 2 times 1 plus 3, which is going to be, that's just going to be 3 minus 2 plus 3, which is 3 minus 2 is 1, 1 plus 3 is 4. So I have the point 1, 4. And I find the slope between those 2 points. So I'm going to do 4 minus 19 over 1 minus -2. 4 minus 19, that's -15, and 1 minus -2 becomes 1 plus 2, which is 3, so -15 over 3 is -5. So this is the slope of the secant line that goes between these 2 points on the curve. Next it says find an equation of the secant line containing the 2 points that we just found, -2, g of -2, and 1, g of 1, which is just exactly the points I just talked about. How do we find the equation of a secant line? I'm going to show you 2 ways. The first way is probably the way that I usually do it. I just do y equals mx plus b. And I know my m because I found it just a second ago. My m is this. That's m. What about my x and my y? Well, I just use any point on the line. So in this case, I could use -2, 19, or I could use 1, 4. I'm going to use 1, 4 because that's a little bit simpler numbers. So I put a 4 in for the y. I put the -5 in for the m. I put the 1 in for the x, and the b is the only thing I don't know. So I can solve for that. So 4 equals -5 plus b. I add 5 to both sides, and I get b equals 9. So now, the equation of the secant line is going to be y equals -5x plus 9. That's my y equals mx plus b equation of that line. That's called slope-intercept form. There's another way to do it using something called point-slope form. Okay, point-slope form for a line. That's y minus y1 equals m parentheses x minus x1. That's point slope form, where m is still the slope and the x1 and the y1 are the coordinates of any point on the line. So again, I'm going to use the point 1, 4. So I'm going to say y minus 4 equals m is going to be -5, and then x minus 1. Then I just distribute and carry this out. I could leave it like this, but I'm usually going to have to get it into slope-intercept form anyway. So y minus 4 equals -5x plus 5. Then I add 4 to both sides to get y by itself, and I get y equals -5x plus 9, which is the same thing I got when I did it with the slope-intercept method. All right, part C says, using a graphing utility, draw the graph of G and the secant line obtained in part B on the same screen. So I'm going to pause it and go ahead and do that. Okay, so you can see I've already typed into Y1, I typed in the parabola, the original parabola equation, And in Y2, I typed in the equation of the secant line that I found in part B. So I'm going to graph both of them. I went ahead and did my zoom to the standard zoom window. And there it is. There's the parabola, and there is the secant line going through the 2 points that were mentioned. I can't see it very well, so maybe I want to change my window. I'm going to increase my Y max to, let's try 30 and see. Yeah, now we can see it pretty well. The parabola and the secant line passing through 2 points on the parabola. And that's it for section 3.3. Good luck on that assignment. I'll see you again in 3.4.